So this session is a gap node. Is a gap node coming near you? And so up here you have myself, Matt Petersen. I'm Vice President of Access Architecture for Charter Communications. We have Bill Beesley he's a Principal Architect with Fujitsu. And then Roger Stafford, he's a Principal Engineer from Charter. And so Bill's written a paper called MSO Strategy and Planning Lead, all about GAP, DAA, edge compute, fog compute, as well as Roger has written a paper on gap node, what's in it for me. And so we're going to start off with Roger. He's basically going to help tell us, why the gap. And essentially, Bill's going to follow up with Roger and tell us, what's actually going to go in the gap and how. So I'm going to turn it over to Roger. Roger, would you like to?
Hi, I'm Roger Stafford, and good morning. Thanks very much, everybody, for attending this session on distributed access architecture and the generic access platform. I wanted to present a paper today that examines how the platform becomes a viable economic alternative to traditional node designs and the deployment process for MSOs. But let's start talking about what the generic access platform is. So the generic access platform is an outdoor housing enclosure that can be built into a number of ways to address multiple distributed access architecture applications. What I wanted to propose here today is how gap housing is a better alternative and to explore those economic factors that make gap advantageous. Distributed access architecture has been an industry initiative for well over 6 years now, with companies developing nodes for this emerging market. And DA introduces the concept of remote physical layer nodes to convert deeper penetrated digital fiber into HFC radio spectrum and deliver it closer to customers' homes than previous network design and deployment approaches have done. So the gap housing can be used for other applications beyond just an RF node. It's also intended to standardize the housing design for other outdoor equipment such as 4G, 5G, small cell radios, Wi-Fi access points, remote OLTs, ONUs to support EPON and GPON networks, edge compute nodes, smart city applications, IoT radios. So really an absolute multitude of different applications, and I'll go into why we think that's important. So this greatly reduces the need for multiple node housings on the same coaxial strand. We've already started to see a progression from simple HFC amplifiers to a myriad of other network edge applications, combined with an increase in the available bandwidth across the network. And we have identified a need for a universal housing to put all of this hardware into. So increasing bandwidth is a driver for this. If we do as been done traditionally, is keep doing node splits, then that increase in bandwidth, as we all know from the Nielsen curve, drives us up from 1 to 2 to 4 nodes. And with a compound annual growth rate of around about 40–45%, we're basically doubling bandwidth every 2.8 years. So that's an enormous growth just to keep up with current bandwidth progression. But then if we look at mobility services, the need for driving mobility into the field with citizen band CBRS services at 3.5 gigahertz, then we see a greater need for more types of nodes. So developments are ongoing in the mobility market to design and deploy radio access networks with small pico and femtocells to add to this emerging infrastructure. Additional housings are going to be needed for smart city applications to enable sensoring and monitoring devices such as IoT radios and surveillance cameras. We're already seeing cities come to us asking for those needs to be addressed. So these monitoring and sensing applications are still emerging, but there's no doubt they will continue to increase in number and will drive the need for more network node connection points. Higher traffic capacities and lower latencies are normally achieved by placing nodes closer to user groups or customers, and all of these need more nodes, where the ideal location is outdoors and on plant. So really we're at the start of what we think is going to be a large upscale in the number of nodes needed in the field. So from the start of this project, we wanted to appeal to all industry segments that can ultimately benefit from a standardized housing. So it's applicable to the telecom service providers as it is to the cable providers. With a gap housing, we move away from customized housings to a standardized modular approach. Perhaps I can share an analogy with what went on in the 1970s and 80s with the development of the personal computer. I think this is a very parallel analogy. The first computers of the 1970s and 80s were customized designs that integrated all of the necessary components such as the CPU board, onboard memory, a VDU and a keyboard. But it became apparent that the rate of development was being slowed by the sequential design process involved in producing a single PC of that type. So it didn't scale very well. So in 1985, the advanced technology form factor, the AT platform, was developed as a motherboard with common interfaces that could be housed in a standard chassis. The AT motherboard could be equipped with LAN cards, memory modules, disk interface cards, and other peripheral devices. So the development then centered on incremental improvements for each of the peripheral modules, using the motherboard as a common base. Over the years, the motherboard capabilities were increased, but there remained a backward compatibility in terms of supported standard interfaces. The development process moved from a single vendor being the only developer to a multi-developer environment with a high rate of new product availability. So the GAP project is essentially leveraging the same idea with a similar approach, where the cadence is being exchanged for the ability to develop a technical functionality while retaining as much existing hardware as possible, and thereby so lowering the operational expenditure of service, for service providers. So, by going from a myriad of devices on the strand, we go towards a single module that can do multiple applications. So, how did we conceive of the GAP as a physical device? The most important thing is the housing. The housing can be reused. It's divided into a number of modules in the lid and the base. The standardized slot sizes, so that we can accommodate the things that are definitely needed, the power supply. There's a high-speed backplane. We envisaged two types of backplanes for this. A high-speed backplane for data transfer at high speed using PCI Express 4.0. And that can be upgraded. It's in itself a module that can be removed. So we can get to, say, PCI 5 or 6 when those specifications come out. The idea of a slot approach means that we can swap out modules as needed. New modules can be designed into those slots. There's a power plane, which is again a replaceable PCB. And then there are ports that are usable for different applications. It could be basically an entry, but it could be used for coax entry, optical entry, or for to take feeders to antennas. So in this paper, I break down the traditional node and look at how the node is developed today. Because the GAP is intended to replace additional node. So I broke down the development process and the deployment process with an MSO, a telecoms provider, into two separate blocks, then economically modeled those two blocks. So there are a number of activities there. I'm not going to go through all of these blocks, but just to call out the last one, with a traditional node, ultimately the MSO has to discard it. It's not reusable at all. It was a custom design for a specific one use purpose, and it ultimately gets disposed. What I looked at for the gap node is to compare the development model. Just want to get this to go forward here. There we go. So I drew up a similar flow diagram for the gap node to see how that would compare, taking again taking into account the OEM design cycle, the node vendor design cycle, and then the MSO cycle. The important thing here, the green boxes basically show that it can be recycled and redeployed. That might be, in the simplest case, that a module is replaced just for repair purposes. Next level up from that would be the node is repurposed whilst it's still on the strand by putting new modules inside it that have been pre-engineered and tested to fulfill that new application. Or in its more work-intensive state, be taken down off the strand, reworked in a warehouse, and then tested and put back into the field in a completely different incarnation. So the reason for breaking those cycles down was to look at the cost elements to this. And what the paper really concentrates on is the economics of how those two, traditional node versus gap node, compare. So I won't go through all the factors, but read the paper, you can see what into it. I'll call some of them out as I go through. So if I look at the traditional node versus gap node vendor cost, this is the design cycle for the OEM. The customized housing design that had so much put into it to design that customized housing, it's a different housing for every node today, that goes away because it's already designed with a gap housing. You're reusing a mechanical structure that already exists. With predefined places for those modules to sit. So most of that design work goes to zero. The customized component design is much more simplified because it's not a design from scratch each time for the trays that go inside that node. So it doesn't go to zero, but it's much reduced. The third-party component design, each vendor is using third parties for some of those subcomponents. That essentially goes to zero as well. The prototyping costs, there's always prototyping still involved. With any new module, there has to be a lot of prototyping work goes on to that, but that also gets reduced. But an interesting factor here is that the unit cost is not parity. It looks like the unit cost goes up, and it could be as much as 15% higher. So the cost of a node does appear to go up. However, what I'm going to look at in the next slides as to why that's still an advantage to MSOs. So this is a set of costs that an MSO would incur in the deployment and sustaining of a node in the field. And it basically it looks at field trial setup, training for tech ops to deploy nodes, the unit deployment costs, i.e. the amount of capex it took to buy those nodes and put them out there, the connection of a node on a strand, the splicing costs, annual repairs whilst nodes are in the field, disposal costs of those nodes, capital write-off. So those are all built into the model. So all the bars on the left-hand side represent those items. On the right-hand side, that's the total cost of ownership for an MSO to have that device in the field. And I basically modeled this on a large number of deployed nodes, about the same cadence as we're going at today, with a bit of an increase to show year one type of costs where we're deploying more nodes than we had done in the previous few years. And basically just to model that uptick in penetration of gap nodes. But basically, overall, you can see that total sustaining costs, as represented by that bar on the very right-hand side of both graphs, is that it's about, it looks like it's 50% less expensive to deploy a gap node for an MSO or a telecoms company compared to traditional nodes. So for that model, I built in a set of assumptions which you can see in the paper. The one thing I wanted to call out was that the model is optimistic with that 50% figure because it's based on the simplest upgrade for a module function based on, and the repair based on a single module being replaced. In reality, there's going to be the need for more modules being replaced in a module during an upgrade process. So I looked at those as well. So those are discussed in the paper. That kind of reduces that 50% figure quite a lot, but but nevertheless is an overall saving even for an extreme upgrade of a node. So with that, I encourage you to read the paper and look at more details, but that's all I've got, and thank you very much.
Good morning. So it's always telling when you see a session this full. You know you're probably working on a really crazy and radical idea if everybody shows up to find out what's going on. So Roger's kind of told you sort of the economics around it and sort of some of the reasons why we want to gain some efficiencies in moving away from one-off built platforms to standardized platforms, and sort of historically that's the way the industry's worked. I mean, he talked about the ATX. We also see that in other areas like open compute, or even something simple like in the 19-inch form factor, right? It's very standardized. It's something we all understand. I have a question for the people in the room here. So just for show of hands, how many people work for an MSO? And then show of hands, how many people work for a provider providing services or equipment to MSOs? All right, so what I'm going to attempt to do in the next 15 or so minutes is tell you why all of you guys should care about GAP and why you should be as excited about it as those of us that are working on it. So, excuse me. Roger touched on Nielsen's law, and this was a sort of an interesting observation about bandwidth consumption at a user level, not in the network level. And Jacob Nielsen in 1998 realized that he considered himself a fairly high-end user. And by the way, if you're using ISDN in 1998, you probably were a high-end user. But he went from 1983 at 300 bits per second all the way up to 128K ISDN in 1998. He essentially observed that my bandwidth grows 50% year over year as a consumer. And he revisited his paper in 2018 when he now has the good cable modem, and it still holds true. So his observations have played out over time, but we have to remember that not just bandwidth is growing. If we have to grow bandwidth in the network, we're also going to grow our space and our power. And now you're hearing in all the sessions today, all the gamers and the IoT guys and the self-driving cars and the 5G, they all want lower latency. So they're going to make it even more complex for us. And that drives cost. And so what we're seeing is, by the way, I have not observed that real estate's getting any cheaper. So if you guys counter that one, please let me know. So what's happening is the industry is now rethinking, I've got to make these head-ends more space efficient because they're growing way too fast. I'm using up all my space, all my power. I cannot stuff enough gear in there to push enough bandwidth out to the edge. So what we do is we start pushing more things to the edge. We push the digital electronics out closer to the consumer so that now I can conserve the bandwidth, I can conserve the space and power, I can lower the latency by getting the equipment closer to the computer. By the way, the session before asked a really interesting question. I'll ask you again because I'm now thinking about it a lot. Where is the edge? That's an interesting thought, especially as we talk about gap. But here in moving remote PHY, it's actually just a way of freeing up space and power. I'm going to basically take these really large CCAP systems that are, 13, 14 RU, 800 millimeters deep. They're using lots of power. That's a lot of transmission gear. I'm going to turn them into virtual CMTSs running on COTS, and then I'm going to push all the transmission equipment off the edge. I'm going to free up space and power, and then my transport's really simple. It's Ethernet over fiber. Right? Sounds good. So why am I doing that? This is called the DAA architecture, the Ethernet over fiber architecture. So the immediate need for DAA, as we observed it and talked to MSOs, was I want to do remote PHY. Okay, we get it. Yesterday was the time I needed to deploy to remote PHY, and all my bosses at the VP level are saying, lower the cost, lower the cost, lower the cost, to get that stuff out of the head end, get it going. But long term, if you push Ethernet out to the edge, all the way to the node and close to the customer, there's a lot more that you can do with it today, or do with it then that we're doing today differently. And today, if you look at MSO networks, they're kind of a layer cake. I have a layer that's providing business services. I might even have an additional layer providing cell tower backhaul. I'm going to have a layer that's providing my own transport for things like remote PHY or my video between my head ends. I might have Wi-Fi backhaul, and these are often different groups, different layers, different NOC management systems. But if I've got Ethernet out all the way to the edge, that satisfies the need for all these use cases. So why have separate networks? The answer is you don't need to anymore. There's no operational capital efficiency in having those things segregated out anymore. Because with network slicing and time-sensitive Ethernet and low-latency DOCSIS, we can serve the needs of the really heavy users, and we can give the general users what they want as well on the same network. So therein lies some of the advantages that where the magic in long-term over gap comes into play, at least from my perspective when I first was approached a little over a year and a half ago by Matt and Ned Dialag at Intel. And I got really excited about it because I said, we could do so much more than this. If I take a platform that's standardized, and I set all the physical, thermal, and mechanical settings for the housing itself, us as a manufacturing, we don't have to do that anymore. It's already defined for me. I can find lots of people making them already. I can buy them. And it's one set of design requirements I no longer have to do, which means I lower the cost of developing my product, I get it to market faster, and here's the really good one. I know we're here with MSOs, but I keep pointing out to the GAP committee, I broaden my market. There's no reason why an outdoor, temperature-hardened, common use platform can't be used by the telcos or the data center guys. Everybody wants to push stuff closer to that theoretical edge, which means we need more stuff to go outside in not friendly environments. So one of the things that I also thought about in GAP, the use cases that were immediately obvious were the things like putting radios out at the edge, or putting perhaps my MUX ponders out at the edge closer to the customer, and so I don't have to do passives all the way out, or I'm going to put some new piece of equipment that I'm going to deliver services to in the GAP housing. Sounds pretty obvious, right? But there's one other service that's coming to the network, and that's actually compute as a service. So anybody heard of Google Stadia? It's supposed to launch this week. You have a paper on it. Of course you heard it. Google Stadia is going to move gaming into the cloud. So no longer are you downloading these enormous games and breaking my bandwidth caps. I don't have to do that anymore. I can now just play the game, spin it up. But for that to work and have low latency, that cloud can't be in Seattle and I'm in Washington. It's going to have to get closer to the customer, all the way in the node. And this is this idea of fog computing. Now, we heard of cloud computing. We obviously have to have another generic term that means somebody else's computer, right? So fog computing is just the idea the cloud's way up here. I'm living in the fog, if you ever had to walk in a foggy city. So I'm pushing some of that compute down to the edge, in this case, in the node, really, really close to the customer. So I slice off a virtual machine or a function, perhaps my gaming function, and I spin that up on the fly. Now none of that bandwidth has to traverse over the HFC network. It doesn't have to go back to California. It's right there running. I got lower latency, higher bandwidth. The consumer has a better experience, and there's lots of uses you can do for this. Some of the low latency things that are coming up, driverless cars are really interesting. They need low latency, and they need to work every time, because I ride a bicycle and I don't want to get run over by one. Thank you very much. But some of the IoT stuff, like the example that was given in the previous session where I have cameras in my house and they're uploading all the time to the cloud. Well, where does the cloud have to be necessarily? It could be in my node. That would be okay. So now you have this idea of not only being able to do the traditional transmission services of voice, video, and data that we've been doing for decades, but now we have new service opportunities in our network where we can put compute modules in and sell them to the highest bidder. The IoT guys, the gamers, all those people. It's a new service and a new opportunity out of this housing. So not only the manufacturers like us care, now you should care as well, because GAP will give new service opportunities. Okay? So, conclusions here. This Ethernet transport for DAA, this 10 gigabit line, is useful for a lot of stuff that we're selling to our customers. We can reuse this network and we can get economies of scale in operations. GAP's going to standardize the service edge delivery modules. Now, us, as a Fujitsu, as an equipment vendor, I don't have to worry about any of the other stuff that's traditionally out in the node. I don't have to do thermal modeling. I don't have to worry about power supplies. I don't have to build backplanes or cases. I just have to build modules. I can do it cheaper, faster, and quicker, and new services that you guys can use. And there will be other opportunities that come out of this as well. There'll be opportunities to provide validation and certification. And then, of course, there's obviously going to be new modules that we haven't even thought of. Some kid doing his PhD thesis right now is going to look at this and go, you know what I could do with that? And it will be something we weren't clued in on yet. The disparate networks have to converge. Much like we have to lower our space and power, we've got to lower the operations and the capital cost of our networks. Deploying a separate network for every single service is not efficient in any sense of the imagination. So again, think about this beyond just a standardized GAP platform. Think about this as an opportunity. One, as an equipment manufacturer, you can get stuff quicker to these guys. And then you guys can sit there and say, look, I can now make more money with my network. With that, thanks.
Thanks, Bill. Thanks, Bill. Thanks, Roger. So I guess, some questions that I have after reading your papers and seeing everything. So I guess the first basic question, and I'll give this one to Roger, is really around the specification itself on GAP. Since you're the co-chair, you and Kevin have been driving this. When do we think, realistically, we'll have the spec kind of wrapped up?
Yeah, I think, we started the specification development quite early on this year, and we have about 25 to 30 people contributing to the specification actually since the beginning of the year. And actually quite a few of those people in this room, thanks for attending. So we still have quite a bit of work to do, but the important point was to get the mechanical definition done first. And we're a long way down the line on that. As you'll see from the demos that are on display with Cisco and in the ATX booth and the non-working prototype in the Intel booth, that we've managed to pull off that hardware definition well enough to move forward onto the next step, which is the module definition. But we're hoping to wrap that up within around about during Q1 of next year, by the end of Q1 next year, so that we can start producing these nodes.
Great. And then, Bill, from like a vendor perspective, when do you think, once the specification's all kind of wrapped up, when do you think like commercially available modules, the GAP, this technology that we've been working on, when do you think that's going to be readily available?
I think that really depends on the complexity of the module you're trying to design yourself. I mean, obviously, if I have to do something that is highly dependent on thermal modeling and knowing what I got for my connection to the outside heatsink, I kind of have to wait a little bit. But if I have something that I can move forward with less risk, once I know what the general mechanical outlines are and they're stable enough they're not going to change on me, then I can get started with my design. But you see modules. If you have a module, for instance, that's going to have a lot of reuse of components we've already designed, we're just repackaging them. That could be a 6-month exercise from start to finish. If it's a ground-up thing, and then we're designing something really fancy and new that's never been done before, that can take a year or more.
Okay.
So the sooner we get the mechanical thing laid out, guys. I know I keep saying that on the call.
Roger, does this, do you view GAP enabling non-traditional vendors in the marketplace?
Oh yeah, absolutely. The idea that you can do developments within modules means that we're separating the design work out into different functions, and really what that means is that someone that did power amplifiers can produce power amplifier modules. That can be coupled with someone that, say, does the other components of a node. So things like power supply vendors, they can individually contribute with their own modules. Basically, it opens up the development and the production of modules to non-incumbent node component vendors, for sure.
Bill, I mean, with what Roger just said, though, as we build all these different modules, you know, what do you think as a manufacturer, what are the largest obstacles that we're going to run into?
Well, thermals are one. We have a fairly constrained thermal budget, and we want to do a lot with it. So that's going to be one of the challenges. But I think really, as we define the standard and we sort of free up the development effort that it takes to design something that provides a function down to just being a module, I think that actually lowers the barrier to entry for manufacturers to get things out there. And you can also, I mean, if you think about it, it's very similar to the way we've deconstructed or disaggregated the transport network. You know, we used to have the line systems and the ROADMs in one chassis, and that's now been broken out because it's really efficient to do it that way. Now we even have things like open line systems where you can use anybody's ROADM over anybody's transponder. That same thing happens at this layer. It really frees up the market to add new technologies and new capabilities. And then for the MSOs, it lowers your cost because the more competitors you have in the space building things, the cheaper they become.
Roger, what do you think the biggest opponent to GAP is going to be?
I think there's a large amount of industry momentum right now towards traditional nodes. Clearly, GAP is a breakaway from that approach. I think over time it will become obvious as node vendors try and keep up with the expanding applications that direction will change, momentum will change, and we'll see an adoption of a GAP platform. But it's really traditional vendor momentum. There are a lot of nodes being produced right now, and we have to get those over to a GAP structure.
Gotcha. Bill, you touched on this a little bit before around GAP being maybe not just a pure cable play, might have a telco play or data center play. What other potential industries are you thinking that you guys could actually market the GAP to?
There are any number of industries that need to put transmission equipment into unfriendly environments. And if anybody's ever been to Phoenix in the summertime or Saskatchewan in the wintertime, those are pretty unfriendly environments and they're really challenging. To the extent that GAP can produce a standard compliant way to deploy these things, and if we just think about doing things like, you know, the first line of thinking was, we'll strand mount it, we'll strand power it. And I said, well, why don't we AC power it? Because the telcos don't do strand mounting, they mount on poles. So if we could do that, now we've got a much larger industry to sell to. And the more broad we can make this, and the more global we can make this thing in terms of the standard and the specifications, the more it lowers the barrier to entry and the cost to develop things. And it also de-risks it for the manufacturers. So it's good for the industry all the way around, because as manufacturers it de-risks us, because now we can take something we design and I can sell it not just to an MSO, but I can sell it to a telco or a data center operator because they have use of it. And then for you guys, it basically lowers the cost of it, because the more broad something's accepted and the less it's unique and purpose-built, the lower it costs to make.
Rajiv, I think you were going to have a question for Bill on that.
Actually, for both of them. So Roger mentioned savings. So I had a two-part question. So what was the time period that you had considered to derive that 50% saving? And the second part was, what did the assumption about single module failure was not true, and what would the saving be over that time period?
Yeah, okay, good question. So I did the model over a 12-month deployment period, and it was based on a ramp-up compared to what we're rolling out today. There was an assumption of a 1.8% failure rate on nodes, which is the best data I could get for an MSO. That seems to be an agreeable number across MSOs. And sorry, what was there was another part to your question.
So if the single module failure was not like there were multiple modules,
Oh, yes, okay.
what would the savings be?
Yeah, that's so I took an optimistic case that a repair would be an upgrade could be done with a single module upgrade. That is definitely the most optimistic case. Reality is that there's a blend of modules would need to be upgraded, but the intention is to have power supplies, for example. Backplanes would remain the same, so not all of the components would change. It may be 1, 2, 3, or 4 of the modules would perhaps change. So I did do a breakdown of that, but I didn't thoroughly model all that. But it does reduce the 50% number down. But like I said before, nevertheless, the savings are very significant, I think.
One thing, you talk about module failure. We did have a lot of discussions around providing the option for redundancy for things like the power supplies and the modules, should the operator want to do that. That's a cost and a risk decision that you'll be able to make in the GAP platform. So you can do a single power supply, you can do dual power supply, whatever works.
Yep. Ron, please.
Hi, Ron Wolf from Charter Communications. I think I saw 11 slots in the platform, meaning that you could potentially have 11 modules from 11 different manufacturers doing 11 different things, and they could be in identical order to another duplicate of that, or they could be mixed together at random, probably not with infinite flexibility, but to some extent. What's the plan for mitigating a failure to coexist, right? There's RFI or EMI, or two different modules don't work together. It seems impractical to be able to qualify a particular module or a particular manufacturer's module with every other conceivable combination of other people's modules that could be put in with.
Yeah. Go.
So that was discussed quite a bit, and especially the old school RF guys that are on the committee. They're very cautious to us that don't do RF, to remind ourselves that RF's hard, and even little things like a 5-volt power supply can wreak havoc on RF transmission. What we envision is this: there will be a need to certify or qualify to some degree a solution. So you're going to say, I'm going to have an RPD, I'm going to have a transponder, I'm going to have a Wi-Fi radio. It's obvious somebody will have to certify and qualify that. Who does that is really up to the MSO. For instance, if you want to take that on yourself, that is a function you could do. You could have your team of engineers say, here's our standard production environment, or the 6 different variants of it, and we certify and qualify those. That's actually open for possibility. But there will also be the capability, there are companies, Fujitsu does this as well, we'll actually take an endpoint solution that's multiple components, and we can certify and qualify that for you. So there will be vendors, and there are vendors out there that can do this today, and can take that on and say, all right, what you've designed here, FCC is not going to get kicked in the pants when you put it out on a strand. Does that make sense? By the way, I did want to also add, you see 11 slots here. We don't actually know how many there are yet. We're still working on that. But also, we don't envision, now initially there will be one size, because that's where we're going to get across, we're going to do agile development. We're going to get across the finish line with one. but there's really not a constraint that says somebody who makes housing could make a 3-slot housing, sort of a mini install for applications where you didn't need all that space and additional modules. So even as long as the slots in the backplane and everything lines up and the mechanicals are right, there's no reason why you can't size it up or size it down.
Perhaps I could just add to Bill's comments there in terms of the compliance aspect. It's something we have given quite a bit of thought to, and most MSOs, of course, are not geared up to do compliance testing at that kind of component level. So Bill covered the idea that a company could offer that as a service as part of the node construction process, and that's very much like the traditional node model. But we think that there's also room for a test house as a test house service, so that module builders can go and follow a specific test plan that will root out any non-compliance items. So yeah, that's something we're thinking about doing.
Yeah, that's a good point. I think we have another question, please.
Yeah. Knowing that MSOs will want to optimize the functionalities into those nodes, what's your thought about test and measurement instrument for field maintenance on that side?
So
do you think is there any place for that, or even the architecture inside it?
yeah, so
Business-wise and technical.
I got a very similar question yesterday. You know, if you thought about the operations, and that's an interesting question that always comes up. You know, usually the technology guys look at stuff and go, "Wow, that's really cool. We can do that." And the ops guys in the corner going, "Are you kidding me?" Right? So you have to think about that. So yeah, there will be. The operations will change, and I think in a session I gave yesterday, we're asking a lot of our technicians who have to go out and operate in the field, and obviously this adds additional complexity to their world. But there are a lot of papers and thoughts around that here about how we can do more to empower our technicians, give them better tools, give them their better ways and processes and procedures. And when I say better tools, they're actually new tools that are going to come out. There's things that we really haven't thought about. There's all this analytics. There's all the machine learning. We have augmented reality. I mean, the idea that you can put on an augmented reality headset and look down at the ground and say, that's where it's buried. I mean, that's going to change our industry, and that's, to some extent, this will also be a driver of that as well. Those of us that make stuff, hey, here's a chance for us to make some really cool things to make their lives better and make the operations better.
Roger, besides the savings that you presented here today, is there additional savings you see with CAP?
So yeah, in terms of cost factors for additional savings, so it looks when I did this analysis, and I mentioned during my talk that the cost of a node could go up by as much as 15%. I think we've seen since then that cost adder is eroding. It's not as much as that, so that's kind of good news. That helps GAP as a project enormously. So that's really one significant item for unit cost. What I didn't model was power consumption from additional nodes, and that's an important factor, I think. But that would happen. Power consumption for an increasing number of nodes would happen anyway. What we can do with a GAP node is, especially if it's a compute node, is that we can look to, say, the SCTE standard for APSIS 216, which is power saving. So we can do bring down of the compute function to lower power consumption as part of the Energy 2020 initiative. So there are factors like that we still have to look at.
Gotcha.
Yeah, I'll just add, I think the observation that the cost initially might be higher, I think most of that's because we're going to do more in that node. So the functionality is greater. So I would expect the cost will go up. But as more people get into the industry and get involved in it, and more people are making things, the individual components will commoditize over time. We see that in every part of our industry, whether it be, you know, routers or open line systems, those kinds of things. It just happens. And so over time, this will continue to lower the cost of these outdoor plant systems that we're putting out there, and then give us increased functionality that we can make money with.
Roger, what's your perspective on the node increase? Or the cost of the node increasing, the unit cost itself?
The unit cost, yeah, like I said, I think now that some of the component providers that were working on the demo units that you see at ATX, Cisco and Intel have had a chance to construct one of these, they're definitely seeing lower costs. I agree with Bill entirely that the function of a node now, in some cases, becomes a dual function node. Really for not much additional hardware cost, actually a net saving if you're doing two functions compared to a traditional node. So yeah.
Gotcha. So I'm really curious. So we have three prototypes. We have a prototype at the Cisco booth. We have a prototype at the ATX booth, and then Intel has a third prototype in their room over in room M8. I'm kind of curious, by a show of hands, like who's gone and actually seen the prototype? Not that many. So I would highly recommend take some time, go over to the Cisco booth, go over to the ATX booth or the Intel booth, and take a look at it. It's real.
Well, Intel has a meeting room.
Oh, they have the meeting room. Sorry. So either Cisco or ATX. You know, it's machined housing. We actually have real modules inside the gap itself. We have modems up online running. Cisco put their cloud native software stack on it. And we have the AOI RPD actually running. So it's coming along, and so it's pretty cool to go and check out.
It's neat that we built a prototype, and one of the things that several of the manufacturers sitting there brought to this is sort of introducing Agile into a standards development practice, which to my knowledge has never been done. All the standards I've looked at took a long time, and they were very waterfall based. And so we're doing a lot of this. Let's just make something or write something down and get comment. And that was sort of the thought process. I will say, even when I saw the prototype for the first time, me and the design engineer from Intel were sitting there going, if only we would move these connectors up just a little bit more, we'd clear out all this extra space for thermals. Oh yeah, we can do that. And so what I would encourage you to do is not just go look at it, but join the activity, join the standards practice, and give us feedback on things that we could do to incrementally improve that. It's this crowdsourcing of ideas that's going to make this thing really cool in the long run.
I think just to add to that, the people that did contribute to those prototypes were very surprised to see how fast it came along, because there were a number of collaborative companies all working together to produce those prototypes. What they found was that they were able to turn it around in just a matter of weeks. The design work had been done really over a matter of months, but putting together those prototypes was just weeks long. It's quite impressive.
So do we have any other questions from the audience here? Please. Sure.
With regards to your cost model, I've been about 8 years at an MSO, now I'm on the vendor side, but I've seen firsthand I don't even think this thing's on, there we go. I've seen firsthand the time it takes to deploy a new node, and then the delay in getting customer service, and the cost that can add up, delaying, installing those circuits that the MSO has. Sometimes they even lose the customers, lose the contracts altogether. Did you guys look at the time it takes to deploy this gap node versus a traditional model? And did you include that in your cost savings estimate? Because depending on how long it takes to deploy the gap node versus the traditional node, and how much quicker you can get service to your customers, you might see an additional huge savings.
Yeah, that's a great question. I did look at the time element of it. It's kind of described in the paper of the life cycle of a traditional node versus a gap node. So one of the factors was that a gap node can be repurposed much faster than a traditional node can be developed if you're leveraging standardized components. If, however, there's a new feature, an absolutely new function is needed, then that's going to take some design work which will be modularized. And sure, that's going to be a longer development cycle than reusing an existing module. But the win is that you don't have to consider all of the other elements around that node because there's an existing power supply in most cases. Though if it involves RF, then there'll be existing power amplifiers that can be used. So the amount of design work is less. And really what that translates to is a faster cadence to address those customer solutions ultimately. And you can see cities are, like I mentioned, cities are knocking on our doors right now saying, can we address this particular application for a particular radio type for an application? And I think we could respond to that a lot more quickly, especially in the mobility market where one module might be an IoT radio, but we could swap it out with a CBRS radio module, or we could put both in the same unit and address two parts of the RF spectrum. So there's a lot of flexibility there. I think that's faster cadence ultimately.
Yeah, think about it. I mean, the mechanical activity of cutting in a node into the hard line probably won't change significantly because that's still an activity that has to function. But because if you look at the gap system, it's basically built on everything as a base where all the RF cuts into, and that stays. That stays long term. And then the lid, where additional kinds of modules we haven't thought of can go into in the future. And then I have a place to splice in fiber. But once I've cut in that RF, and once I splice in that fiber, the fiber tray's there, my RF connectivity's there, and I want to come out and say, somebody says, hey, someone just thought of this new IoT module and we want to make money with it. So just deploy people, snap them in, and then you can even use, if you think about the modules doing things we're already doing in other parts of the industry, things like zero-touch provisioning and SDN control of the systems, overlay that into these types of components and you can turn services up really fast.
Yeah, please, Mohammed.
Matt, Roger, good to see you guys. Looks like a lot of exciting work happening in that space and a lot of great possibilities. Looking at the standards and timing of things, what do you guys think would be the first version of this gap node? What kind of functionality do you see in the first version that could be commercially deployed? And what are your thoughts on the roadmap in next maybe couple of years?
Okay, perhaps I'll take that one. I think I'd like to see it, its first application. I think is a fairly simple one to pull off, and that is a DOCSIS 3.1 cable modem as backhaul to a CBRS radio. I think that's probably the emerging market that we could leverage GAP for. Because I say that because the traditional node vendors are in their first phase of distributed access architecture, where they have got nodes that they want to they want to productionize and gain revenue from, and perhaps there'll be some delay before they switch over to a GAP. I hope that delay is short, but there will be some momentum that will drive it that way. So I think the mobility market, being a new market, will be the ideal platform to start on. There's also edge compute. I think we're really just starting with edge compute. So there are, I think, a lot of applications there that perhaps we're not immediately aware of today, but a few months down the road, we may be there.
Yeah, and I'll just add on to that, right? I think some of the other applications, remote OLT, we've been working with a lot of vendors out there on trying to get more modular components into our existing node base today, and which kind of plays directly into GAP. If we have this platform out in our network and we're able to build a module, we can quickly move fast. So remote OLT, we have RMDs, RMC, RPDs. All these can be modularized to be plugged into the GAP. Ethernet aggregation, as Bill touched on, edge compute. And there's going to be other applications that we haven't even thought of. And I think that's the value of GAP, because we don't know 7 years from now or 10 years from now what are the new apps, and where are we going to need that compute? Is it going to be in a node, or is it going to be back at the head end? And so we want to have capability of being able to push the right application to where it actually needs to be in the network. Rajiv.
Yeah, what's interesting is that as we, the last 5-6 years, we're all moving toward virtualization to a degree. And mix and match has been one of the greatest benefits that we all wanted to get. And what we have learned over the years that, well, my function, my virtual function actually works on my system, so it should work on your system. It's all on x86, it works over Linux KVM with OpenStack, and there it goes. You put it on another system, oh, it doesn't work anymore. Or it works, but it doesn't work the same way it is supposed to. And this continues on to this day. So the question I had, clearly there's going to be more of that, especially when we're dealing with hardware mix and match. So what are the specific considerations that are being put in place to address these kind of mix and match potential scenarios?
So about 6 or 7 years ago, we saw a shift in the industry towards one, as you described in your last part of the question, disaggregation, decoupling components that were normally put together as a system, sold as a system, and validated as a system. So we first saw that. We also saw something that we call the ITification of this industry. And that is because of things like cloud compute, virtualization, we're becoming more like IT guys than we are less like transport guys. And those are the two things that are sort of happening. And the first thing that we sort of realized looking at this about 5 or 6 years ago, both of those require significant operational forethought. That is, it requires a different way of thinking about everything. You have to kind of sit down and think about, well, if I disaggregate these two components, now I have to, they're now separate things. And so instead of managing one thing, I'm now managing two things, or X number of things, right? It can get out there pretty quickly. So we start thinking about things like logically re-aggregating everything, using the software so we can provide a view that's more intelligent and more intuitive to the user. You have to think about things like, how do I validate one, the systems are actually going to work together? Because open sounds great, and we've been doing open for a long time, but any of us that have been working in open often know that sometimes open can have a little bit of pain associated with it, because now I'm the guy that has to make sure everything works together. The good news is it's created a whole new industry of people who provide services who have experience in IT and transport systems and those sorts of operations are now coming in and bubbling up going, look, I can get you started, I can get this stuff validated, I can certify that it'll work, and I can actually show you how to operate it and you can go run it, or I'll be happy to run it for as long as you want me to. So that's, again, it's a new opportunity in the industry to generate value and generate revenue. We often talk about lost jobs in this country. I think it's great when we generate new ones and new industries and new ways to make money.
Fernando.
Hey, one question and one comment. Roger, you mentioned that the initial cost is 15%, could be 15% higher, but the cost over its lifetime would be lower, which sounds good in overall, but the accountants don't always think that way. So for charter, just to say, for instance, are the accountants on board? Are they good with that?
Is the CFO in the room?
You can defer.
I think we've seen over the last couple of years that the engineering element has been able to persuade the financiers of these projects that if we take a long reach view, then they are on board with that type of idea. But you've got to remember that really the bottom line improves dramatically for an MSO, I think, because if you look at the whole operation, and actually that saving was really over a 12-month period, or it's rolling 12-month period, rather than across the lifetime of the product. So the significant savings, I think, will also appeal to those financiers.
Fair enough.
I think it's changing over time. You know, from my perspective, having been also, I worked at an MSO for a long time, now work in equipment manufacturer, and I see, you know, we used to talk a lot about TCO as a value, but a lot of times we got pushback saying, look, I'm worried about my capital expenditures this year, you know, who cares about the OpEx long term, right? I'll deal with that later. I think that's changing. I see the operators becoming more sophisticated in terms of concerns about their financial modeling, not just right now, but how long it takes me, how much it costs me to run this over the long term, and how much money I can actually squeeze out of it over the long term. So I think, you know, there's probably a lot more acceptance to have that discussion, as long as us as manufacturers can provide a clear picture of that and not something that's really fuzzy.
Fair enough. My one comment is, by the way, I run the communications subgroup for the GAP. And part of my interest in that was for exactly what Rajiv mentioned. Okay, coming from a place where we understand virtualization, we know that what really has to be looked at is the interoperability between services. And in the software world, it's software services or microservices. In the hardware world, it's RF lines or EMI or things of this sort. Okay, so part of what I think we were trying to do, or at least in the communication subgroup, is have some sort of robust management and understanding of these modules, right? And what's becoming very apparent, just like in the virtualization world, you need some policy manager. We're going to need some sort of policy manager to be able to do this, because Roger, I noticed one thing that hasn't been mentioned here is what happens when an RMA happens, right? How do you know who broke? How do you know why? And how do you know how to fix it? Right, so there's all these things that really go into the details of the lifetime of the program, and I really do think this is not just a hardware effort. It's got to be a robust software and management effort as well. Otherwise, it fails. So, by the way, Rajiv, always welcome to come join us. You know.
Thanks a lot.
I think you're right. Walk the show floor, though, and look at the manufacturers. Every single one of them keeps talking about the network becoming more intelligent, right? Our equipment's going to become smarter so we can work better, work more efficiently, and maybe perhaps somebody will pop into this room, come back from time to time to stop us all. But, you know, the network is going to become self-aware and more intelligent, and it's going to be able to, it needs those kinds of things that you just talked about. I think we talked about that in the committees. The modules need to be able to talk to each other if they need to. They need to be able to talk to the compute if they need to. They need to be able to talk to the power supply if they need to. And so that's being put into the design. But again, it's not just a mechanical thing. There has to be protocols talking into there, and we have to think about how that happens at a software layer.
Quick question. So the ecosystem of collaboration happened very quickly, rapid prototyping, standards development, and proof of concept. So just wondering, with, say, Charter, can you give us some glimpses on the next iteration of because the standards need to be ratified, especially the hardware specification, as you said. But what glimpses of the next thing that you see for trialing of the gap node?
Yeah, okay, so of course it's an SCTE effort, it's open collaboration, not entirely Charter by any stretch, and it does involve other MSOs as well. But what's the next effort? Well, I mentioned we have to finish the specification. I think we're going to do that in a way that allows us to start using the mechanical details of a gap housing. That gives us some future proofing. Then the module development specifically is the next. Fernando is working on the communications protocol. That's a tougher one, as you got from his from the response as a question there. So we want to bring that together at some point next year. So yeah, we have quite a bit of work to do, but I think in order to use a gap housing, we only really need the mechanical definition to be finished in its basic form. We can deploy in that way first.
Yeah. Well, I think we're
Yeah, just over time.
out of time. Is it quick?
It's quick.
All right, make it quick.
On the notion of scale, what's your thinking in terms of applying or translating the gap concept beyond North America, for instance, to Europe, where you've got different power requirements?
Okay, that's a great question, and we should have touched on that. This phase one is really aimed at the North American market. We really want to do a phase two of this, which appeals to the European market. We have one major MSO that's very interested in that approach, that's what we're going to continue on with for standards development once we've done the first version.
But notice in the prototype, the power supplies are also modular. So if I want to design a power supply for another market to take another, AC or DC input, that becomes a lot easier in that kind of design.
All right, Roger, Bill, thank you. Thank you.